Hi, everybody. We are going to wrap up talking about double replacement reactions today. We started these notes before the break, so you should open your notebook back to where you left off on that last day before school was canceled and all this craziness started. We're going to kind of recap those notes and then add in a couple of other things. Mostly today, we're going to be learning how do we predict the products for a double replacement reaction and how do we identify the states of matter of those products. So to start with, I'd like you to make a few little pieces of paper because we're going to be doing a little bit of playing around. I made mine with different colors so that it's easy to see, but you can easily just like take some blank paper and just like rip it up into little pieces like this and just make 8 little pieces of paper and fill them out just like it says there. So you'll write like PB plus 2, like that. So just pause the video for a second and take a couple of moments to make your 8 little pieces of paper. All right, once you have your 8 pieces of paper, we're going to just recap the notes that we did before break. So we were talking about double replacement reactions. Double replacement reactions will often involve solutions, and that's why we're talking about this kind of piggybacking off of where we were in Unit 6A. Double replacement reactions have this general form. You have 2 ionic compounds who are going to be switching ions. And so I like to use this analogy of dance partners that, like in this reaction, the sodium and the silver will switch so that silver will bond with chlorine and sodium will bond with nitrate and create 2 new products. So I showed you guys this demo in class, but I'm going to show you a short video of it just to remind you. So in this video, you're going to see lead nitrate mixed with potassium iodide. And so both of those are aqueous solutions, and that's what the AQ in the chemical formula means. But you notice that a yellow product forms. And so we're going to try to unpack that a little bit and talk about what the yellow substance is and all of that. So this is a double replacement reaction because there are 2 ionic compounds, and this is a special kind of double replacement reaction called a precipitation reaction. So in a precipitation reaction, you should already have this in your notes, but basically we have 2 soluble reactants. So you saw the 2 beakers at the beginning, both were clear liquids because the ionic reactant had been dissolved into the water. But when you mix them together, one of the products is insoluble, and we call that a precipitate. And so in that reaction, the yellow powder that formed is the precipitate. And so we'd like to be able to figure out what chemical is that, and like how do we know what chemical that is and what chemical is still dissolved in the water. So this is just a quick recap of the solubility rules, which we talked about a little bit before the break. You can find this on the back of your periodic table, so find it right now. And this is basically just a way to figure out for any ionic compound whether it will dissolve in water or not. If in the chart it says SOL, that means soluble. And so as the state of matter in the chemical equation, you would write AQ, meaning aqueous, because soluble things dissolve in water and form aqueous solutions. If it says insol or SSol, that means insoluble or slightly soluble. And in those cases, that would be your precipitate because that's going to be a solid product. So just to recap for you how to use this chart, let's do the 2 reactants from the demo as an example. So if I want to do lead nitrate, I'm going to find lead over on the right side, Pb2 plus, and NO3 minus over on the left side. And if I kind of drag those 2 together, you'll see that's soluble. So that's aqueous. And Ki is also soluble, which we saw in the demo because they both form aqueous solutions. So let's talk about what happens when these 2 things react. So I use my little puzzle pieces, my little pieces of paper to make lead nitrate and potassium iodide. And this is just a reminder about ionic compound formulas that the charges within the formula should always add up to 0. So if you look at this picture, Pb plus 2 needs to bond with 2 nitrate ions, so that you have +2 and -1, and then the charges cancel. Same thing with Ki. K is +1, I is -1, so the charges cancel out. So I'd like you to actually play around with these a little bit and see if you can rearrange your little pieces of paper to form the products. Remember that the positive and negative ions need to switch partners. And remember that the charges need to add up to 0. So you might need to use other pieces of paper. So like I have some extras of these. You might need some extras right now. So yeah, take a moment to play around with it and pause the video right now. And then once you think you figured it out, you can come back and start the video again. All right, hopefully you've played around with it a little bit. And if you did rearrange them, you should have put the lead with iodine and the potassium with nitrate, but you needed to get another I-1 from your pile of papers because lead has a +2 charge and I has a -1 charge. So when we look at it right now, we essentially have the unbalanced chemical equation in front of us. We have the correct formulas for the products, but there's not the right number of ions on the 2 sides. There's an iodine ion on the product side that seems like it came out of nowhere. There's a nitrate ion that sort of went missing. So now we need to balance the equation and make sure we have the same number of ions on both sides. So pause the video again and see if you can kind of play around and make it so that you do now have the right number of ions on the left and the right. Can you make it so that there's equal iodines on both sides? Can you make it so there's equal nitrates on both sides? Pause the video and play again once you figured it out. All right, so here's how I kind of thought through it. I realized that I would actually need 2 Ki's on the left, so that it will, so I'll have those 2 iodines I'm going to need. And that's actually going to make 2 KNO3s. So now if you look at my 2 pictures, I have 2 pink squares on the left, 2 pink squares on the right, 2 yellow squares on the left, 2 yellow on the right, 2 white on the left, 2 white on the right. So this would be my final balanced equation because I needed to add coefficients to get the right number of molecules on both sides of the equation. So you can kind of write this down as a general set of steps for predicting products in a double replacement reaction. First, you need to identify the charges of all the ions, which we kind of did with our little pieces of paper. But when we get into some example problems, I'll show you how to do that. You need to then switch the ions and write the correct chemical formulas for the 2 products. That's really, really important. That's where you have to make sure that the charges will add up to 0. And then you need to balance the equation by adding the coefficients. So the next thing we want to figure out is how do we know which of those 2 products is the yellow precipitate? That's where we're going to need to use our solubility rules. So here's the balanced chemical equation up at the top again. I am going to use the solubility chart to figure out the solubility of my lead iodide and my potassium nitrate. So let's see, lead iodide, it says insol. And KNO3, it says sol. That means that lead iodide is not soluble, it's insoluble, and that is my solid. So the yellow stuff in this test tube is lead 2 iodide. And the potassium nitrate is still dissolved. And so in the clear solution that the potassium iodide is kind of precipitating out of the solution, the clear solution does have potassium nitrate in it. So my final answer of how I would write this reaction would be to include states of matter as well. So I have that the 2 reactants are aqueous by writing AQ. I have that the lead iodide is solid and that the potassium nitrate is aqueous. So one quick note is that if both of the products are soluble, then you need to write no reaction because the reaction actually doesn't happen. If you start with stuff dissolved in water and then you end with stuff that's all still dissolved in water, there was no chemical change. And so we'll look at an example in a moment that's like that. Okay, we're going to do some practice. So now would be a good time to just make sure your notes are all good, that you've written everything down. Go back to anything if you need to, but we're going to do a couple practice problems in your homework packet.